Take a nice chunk of soda to get some energy, then go erase all that calculus. And now we're going to do a very exciting thing for the next 44 minutes. And this very exciting thing that we're going to talk about is ordinals. Is this important? It's a really good question. What does important mean? Probably it's not the most important thing in the world. My first couple of years of teaching this, I did not talk about ordinals, but they do kind of come up, and specifically they come up if you're trying to understand the axiom of choice, another thing we're skipping this year. So literally I'm doing this because it's kind of like cool, but there are applications. All right. What's an ordinal? This is a very difficult question to ask, and if you just go to the internet, you will not get enlightenment. That's because the internet will explain things badly. I think the Wikipedia page has been updated, but 10 years ago it was outrageously, ridiculously bad. Okay, in your lifetimes, the quality of math Wikipedia articles has greatly improved, but find some 10-year-old tweet thread of me laughing hysterically with screenshots of the old Wikipedia article about ordinals. It was incoherent. Fortunately, you have a teacher. Also, fortunately, you have Noah Singer, a great person who graduated 5 years ago, who made this presentation. And it's really high quality. He did it like in LaTeX and stuff like that. What are ordinals? Well, let's go all the way back to what even sets are. Bolzano defined a set. Recall that in his work published after his death is the earliest mention of sets. And in one of his works, he says, I think he was already dead by then, so this might have been published. That might have been the publication date, not the day he wrote it. An aggregate so conceived that it is indifferent to the arrangement of its members. In other words, Bolzano has the modern conception of set. The modern conception of set thinks of it as just a big old bag full of a bunch of stuff. Can I get a gentle head nod in the crowd? Cantor has a different view. A couple of little pieces of vocab here. Of course, all the basic things you need to know about sets, set membership, subsets, power sets, all that stuff. If you give me two sets, then of course we know already that they have, we have this sort of definition for what it means for them to have the same cardinality. We say that they have the same cardinality when there exists a bijection between them. And if there is an injection from A to B, thank you, if there's an injection from A to B, then we say that A is less than or equal to B. And that applies to finite sets and also infinite sets. Well, we assign to each set a cardinal number. That cardinal number represents its cardinality. And if it's a finite set, then it's just the number of elements. But if it's an infinite set, then if there's a bijection with the naturals, we assign it cardinal number aleph dot. If there's a bijection between the set and the power set of the naturals, then we give it cardinal number 2 to the aleph dot, etc., etc. Okay, who's with me? Cardinal numbers are numbers which can be used to describe the size of a set. Okay, but you're permitted for wondering at this point, what's really going on here with these transfinite cardinals? How many of them are they? Are there? What's the relationship between them? All of that is unclear so far in this class. It would be clear after this presentation, but we're only going to do a third of the presentation, so it will still be unclear. If you want to define arithmetic on sets, you can do it using some kind of little sort of, I'll call this a trick. You essentially take every element in A and you tag it with a 0 by creating, A times 0 would be the set of ordered pairs whose left element is something from A and whose right element is 0. In other words, you convert every element from A into an ordered pair, like that element, comma 0, alpha, and then you convert every element from B into an ordered pair, B, comma 1. Okay, this is good because it prevents why is this good?
Because you don't count.
You don't overcount. Yeah, good. Except as I'm saying that. Yeah, of course, duh. Right, so if A and B have some members in common, now when I say the size of A plus the size of B, I don't want to count those members. I want to count those members in common twice. This forces you to count correctly. Who's with me? So you union those two sets together. Okay, this is not really important. All right. Cantor has a whole different view about sets than the modern view. Cantor is a very interesting guy. He feels that sets are fundamentally structured. And in fact, Cantor has these kind of religious beliefs. He has this kind of conception of set theory. And his conception of set theory is that all the sets were like made. And they were made in some kind of like order. And by like God or something. And in fact, we can describe the order in which these sets were made using these things called ordinals. And so for Cantor, sets don't just come as a big bag of elements. They come with some inherent structure to them. So this is pretty plausible with the natural numbers, for example. We don't think of the natural numbers as just a bag of numbers. We think of the numbers as being, natural numbers as being ordered in some kind of way, and specifically they're ordered via the successor relation, successor function. Okay, so to Cantor, that is like the default way of thinking about a set, as being a bunch of things in some kind of order. Okay, and yeah, so let's talk about ordered sets basically. All right, cardinality is kind of a weaker concept because cardinality can only be used to compare two sets as to which ones as to their size. But in addition to the cardinality, if we want to compare two ordered sets, we can assign to every set what's called an order type. All right, this is a little bit difficult to understand exactly what this means, but think of an order type as describing the elements in the set and the order that they are in. And for the moment, I'll tell you that two sets have the same order type if they are ordered in the same way. And to make that concept precise, we can construct so two sets have the same order type if you can make a bijection between those sets, and that bijection preserves order. In other words, if x is less than y, x and y are two elements of A. So whenever x and y have a certain relationship in A, then the elements in B associated with x and y, which are called f of x and f of y, also have that same ordering relation. Okay, I don't want to get bogged down on this. Okay, well, a little bit more. Okay, so the cardinality of a set corresponds to its cardinal number. So we assign to every set a cardinal number to represent its cardinality. But then we also assign ordinal numbers to every set to kind of capture its ordinality, whatever that is. All right, two sets can have the same cardinality, but they have different order types. So this is kind of a finer distinction. All right, well, I'm just going to tell you right now that the first ordinal, or rather the first infinite ordinal, is omega. And we should think of omega as the order type of the naturals. Okay, therefore, still being casual, a set has order type omega if that set is like the naturals. And what I mean by like the naturals, well, it needs to be an infinite set, specifically a countable set. And every single element of the set, comes one after the other. Okay, and the details are there exists an order preserving bijection between the naturals and that set. All right, let's just do some. Okay, I got the naturals. Here they are. Oh, have I been recording any of this properly?
Yeah, it's like me.
Okay, good. All right, so now I guess I'm just gonna go over here or something. Okay, consider the naturals and the primes. So here's 0, 1, 2, 3. How far does he go? I guess it doesn't matter. And now we have the primes. So this is the naturals, and then we have the primes. Well, what do the primes look like? 2, 3, 5, 7, 11, etc. Okay. Now some questions. Can I place these in a bijection? Yes, I can. And here I do it. So there is the bijection. We'll just make our bijections with arrows. Okay, good. Good. Answer, yes. Can they be placed in an order-preserving bijection? Yes. This is itself an order-preserving bijection. What makes this bijection order-preserving is that if any two elements in the naturals have a certain order, then so do their counterparts in the set of primes. Follow? Okay. And so we're now going to say that the primes have order type omega. So omega describes is an ordinal associated with this set. Okay, what about the natural numbers and the integers? Can they be placed in a bijection?
Yeah.
Yes, they can. We have done this before a long time ago. What is the simplest way to put them in a bijection?
0, 1, -1.
Yes. Okay. So when all we cared about was the size of these sets, then we made our bijection like this, right? Okay. So the answer is yes. This is a bijection, and therefore the construction of this bijection proves by definition that these two sets are the same size. In other words, both of them receive cardinal number aleph naught. However, is this particular bijection that I have drawn an order-preserving bijection?
No.
Clearly not. Now you have to kind of clarify now that what I mean by that is the naturals under their normal ordering and the integers under their normal ordering. In other words, I am assuming that we all just agree that the natural numbers come in a certain order. By this I mean the standard ordering, and that the integers come in the standard order, their normal order. Okay, and this is just not order preserving. Is everyone with me? Because look, take two numbers like 1 and 2. 1 is less than 2, but 1 is not less than -1. So in other words, this bijection kind of scrambles the order in which the integers come in. Is it possible to construct an order preserving bijection? Just no, right? Fundamentally, no. If you kind of think about trying to do it, you're like, yeah, that's not going to work. There's just no way to capture the fact that the integers kind of like go infinitely back in the the left direction, and the naturals just don't. Therefore, these are not like the naturals, I guess is what I want to say. Okay, good. Let's actually not talk about the integers again, because they're sort of a bad example because they don't get an ordinal at all. So let me just almost like pretend that didn't happen. All right. Great. So what the hell is omega exactly? Well, I don't want to say, because I want to make sure we get it first before we get into the details. And also we're going to run out of time, so we're not going to get to the details. But for now, just think about omega as a mathematical object. Rigor will come later for the juniors next week. But what omega represents, thank you, is like the structure of a set when it is ordered like this. Okay, so what are some things which have order type omega? Well, the naturals do, but also the prime numbers do. What do we really mean when we say when we say a set has order type? And what is it that we mean when we say an ordered set has order type omega? Well, essentially what it boils down to is there's the first one, there's the second one, there's the third one, etc., and it goes on forever and you never run out. Cool? And you get all of them. Okay, so the powers of 2 have order type omega. Also, this set has order type omega because it starts. It has the first element, the second element, the third element. Is that pretty clear? I could go into more detail. All right. If you wanted to mess with, if you were some evil kindergarten teacher or something like that, you could teach all of your kids to start counting with -4, and they would just walk around all day long saying -4 when they really meant 1. And it would be very confusing, but it would make complete sense within that class. They would just be doing regular arithmetic. They would just have different names for the numbers than you do. Really?
So for everything that is like aleph naught, can that be mapped from integers while preserving order?
No, I mean we've already seen an example where we couldn't, right?
Like the positive negative integers mapping to it, where 2 integers being in order implies that.
Oh, I see what you're saying. Yeah, but not that preserves order. No.
I guess if we go
Wait, let's do a couple more examples. Were you going to say something? There was this really cute viral video that was really popular 5 years ago of this guy and his daughter arguing about how to count to 5. And the girl was like, 1, 2, 3, 5. And he was like, no, 1, 2, 3, 4, 5. She's like, 1, 2, 3, 5. It was really cute. But it got millions of views, and I guess they took it down because whatever. But had the same order type. Okay, let's look at some structured sets and find out their order types. Okay, so consider the naturals and consider this new crazy set, which follow this notation. The notation here is you get 0, 1, 2, 3, and after all the naturals comes A. Okay, do these two sets have the same cardinality?
Yes.
Cardinality. Yes. They do have the same cardinality because, okay, maybe that's not so obvious, but I'm going to make it obvious to you right now because this is 0, 1, 2. What is required to establish cardinality? A bijection. Is it possible to create a bijection between these two sets? Yes, how should I do it? I guess it depends which way you're going. I'm going to go from, I guess it doesn't matter. But yeah, but send 0, first just like take care of this guy way over here that's lurking up like too high. And then, from that point on, just like boom, 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 boom. Okay, good. So by the definition of two sets have the same size, if it's possible to create a bijection between them, I have just created a bijection between these two sets so they have the same cardinality follow. In fact, their cardinality is aleph not. But, do they have the same ordinality?
No.
Certainly not.
Can the second set exist?
Sure, I don't see why not. I just made it. Boom, there it is. Yeah, okay. Let me give a less glib answer. Jeff, I hereby define a set as follows. This set is all the natural numbers, but also some other new character A. Think of it as like a monster. And I hereby define an ordering relation on that set. The ordering relation is, for any two normal numbers, let them be ordered in the normal way, and also I insist that my monster is larger than any natural. That would be the precise definition of the set. Who's with me? In other words, but I'm just going to be more casual by just saying comma, dot, dot, dot. Okay, so this is certainly a set. I mean, especially if you're not worried about things. If you're just like a regular kind of Cantor person, then there's no philosophical problem with this. Do they have the same order type? No. Okay, so I hereby introduce you to another ordinal. This ordinal is called omega plus 1. The omega plus 1 ordinal has been invented to capture sets which are ordered as this set is. Get it? Okay. And so do you see how it's like a finer distinction ordinality? Because these uses have the same cardinality, but they have different ordinality. Okay. And I didn't really give you a chance to answer. How do I know? Does someone give me like a 30-second explanation of why there cannot be an order-preserving bijection between the naturals and this set?
Because A is greater than every natural number, but there's no element like that in the set of naturals. No
that's the perfect way of explaining it. Yeah, A is greater, in this second set, A is greater than every single other element of that set. But you cannot point to a counterpart in the naturals, which has the property of being greater than every other member of that set. Follow? Okay, so they really are just like different. Okay, what about this set? And you're supposed to read this as the set of all the naturals, and then after all the naturals are done comes A, then B, then C, where A is less than B and B is less than C, blah, blah, blah. Is this, let me ask you a question. Is this set countable? Yes. What is the cardinal number associated with this set? Aleph not. What is the ordinal associated with this set? Omega plus 3. Get it? Okay, good. And now, okay, so there are two types of ordinals. There are successor ordinals and limit ordinals. The successor ordinal just means kind of like one more, right? Just kind of like add one. Immediately after successor ordinals come after some kind of other ordinal. Limit ordinals are harder to explain. Limit ordinals are ordinals which come after an infinite number of previous ordinals. Maybe like more on that later or something. Okay, good. Let's look at some more exotic ordered sets. How about this one?
Are they all greater?
Yes, you're supposed to read it casually as like going from left to right, getting bigger. So in other words, what is this? I'll just explain it verbally. It's all the naturals, and then after all the naturals comes another extra shadow set of naturals. Does this have the same cardinality as the naturals?
Yeah.
Of course it does. You can make a bijection by just listing them as like 0, 0 prime, 1, 1 prime, 2, 2 prime. That's pretty clear, right? Here again we have another set with cardinality aleph not. What do you think the ordinal is associated with this set?
2 omega.
Good guess. Even more casually, I would probably just call it omega plus omega. But a choice has been made a long time ago. Omega plus omega, we write this as omega times 2. And you have to be a little bit careful. It's different than 2 times omega.
Are you serious?
I am serious. I am being serious right now, Philip. Omega times 2. Read that as omega, comma, 2 times. Everyone say that. This is good. This is good teaching.
Omega
2 times. So it's like an omega followed by another omega. We call that omega times 2. And the definition of omega times 2 is just omega plus omega, or something like that. Good question. Next bullet point. What is this set?
Omega.
Wait, is it still 0 prime is greater than all?
Yes, we should still read from left to right, right? So this is now 0, then 0 prime, 1, then 1 prime, 2, then 2 prime.
Omega.
What is the order type of this set?
Omega.
Omega. Yeah. Does everyone see that? And so this is actually 2 times omega, because this is 2 omega times. In other words, there's this whole thing called ordinal arithmetic, and in ordinal arithmetic, omega 2 times, it just means omega plus omega. But 2 omega times is in fact equal to
Omega.
omega. Who's with me?
Omega.
Oh, okay. Good, more. What is the order? Yes.
I think it's important to mention it.
Wait. Someone smarter than me is going to say, who also knows things, is going to say something important. What is it?
We should also mention that's also true for addition, right? Like it's non-commutative.
What?
Like
Yes, that is very important. He's saying he would like to alert us to the fact that omega plus 3 is not the same thing as 3 plus omega.
Oh, because that's just omega.
Yeah, because what does this mean? This means like a set that's like omega followed by like 3 more at the end. Whereas this should mean something like 3 followed by a set that's like omega. So in fact, you have another sort of fact of ordinal arithmetic, which is that 3 plus omega is omega. Who's following this? Good? Thank you, Evan. Okay. More. What's that? Careful. There's like a whole set of naturals plus a whole other set of naturals with then just 5 little guys at the end. So this is omega times 2 plus 5. Woo! Okay, what about this? Oh, and notice that Noah Singer, after much deep thought on this issue, trying to keep it casual, but also notice the comma. There's like some interesting things happening here, right? Because it's like there's like the 0th copy of the naturals, and then there's the first copy of the naturals. Then there's the second copy of the naturals. But then that's supposed to just like keep going forever. It's hard to do this without getting into heavy notation. Okay, so what is this? This is omega times omega. Yep, it's omega times. And omega times omega is omega squared. Cool? Okay, well, pretty exciting. Okay, then there's some like hard stuff. An ordinal is a canonical representative of an order type. Okay, so what is an ordinal? You can think of, oh boy. Let's not even do this. Let's just skip to the final bullet point, which is kind of cute. You can think of it. You might be wondering, do Mr. Rose, like, what the hell? What could this possibly be useful for? Well, it's useful if you want to talk about infinite sets, which are everywhere. For example, consider all ordered pairs of natural numbers and order them according to their lexicographic ordering. Do you know what that means? Like alphabetical order. Okay? And so now, how does that work?
Oh, wait, so like...
So like first comes 0, 0.
Wait.
Then comes 0, 1. Then comes...
Oh, I thought you meant like the spelling.
Well, I do mean that kind of, but
So
like...
4 is F.
No, but not like the English spelling of the word. But that wouldn't be exciting, no, Phil. Okay, and then what comes after all the zeros, so to speak? Like 1, 0. And then 1, 1. And then 1, 2. And then what comes after all the ones? 2, 0, and it goes on forever. So this is putting ordered pairs of naturals in like the order, in like alphabetical order by like their like whatever. Okay, good. So you can say that this omega squared is useful as describing the lexicographic ordering of numbers. Follow? Okay, good. More. What is too much math? Skip the slide. Okay, and so it's like this. Here's the thing about the ordinals, man. They just don't stop. They never stop. They keep coming and coming and coming. But as soon as you think you're done, you're not done. You're just beginning. This wonderful picture that someone made a long time ago on Wikipedia is a picture of all the ordinals. We got 0. 1, 2, 3, blah, blah, blah. So that is, those are all just the regular numbers. Oh, by the way, those are ordinals. Why are they ordinals? Because, take the 4 people here, everyone, 4 people at this table, stand up. Please, just really quick. Is there an obvious person? Which one of you is shorter? It's you? Okay, so let's say Joy is shortest. So let's order them by height. Well, what would you say is the ordinal that we should associate with these 4 people? Also, let's say Ryan on his tippy toes is 1 inch taller than Albert. Okay, good. So the ordering by height is like, first Joy, then Claire, then Albert, then Ryan, let's just say. Okay, so what ordinal should we assign to this set? 4. In other words, every natural number is okay, you can sit down, thank you. Every natural number is an ordinal, because it describes an ordered type of an ordered set. And so, think about it though, any set of size 4 must have ordinal 4. Are you with me? Because with finite sets, there's only one way to order 4 things, assuming that they are ordered, which is to go first one, second one, third one, fourth one. And so any set of size 4 which is ordered in the way first one, second one, third one, fourth one, there will exist an order preserving bijection between that set and any other set of size 4.
Is there a bound on certain sets like can be ordered? Like, is there a way to show that the naturals can only be ordered up to like omega squared or something? Like
no, in fact, you can do crazy. Oh boy, no, you can go higher. I'm pretty sure. In fact, I have a handout which we're going to now give to everyone. And if you're tired of talking to me, you can just like do the handout. But okay, let's just look at this. Let's just look at this crazy picture really fast. So here's what we got. All the naturals are ordinals. And hey, by the way, 5 is what's called a successor ordinal because 5 is the successor of 4. But omega is not a successor ordinal because omega is not the successor of any ordinal. In other words, it does not come immediately after some other ordinal. What does it come after? Like an infinite number of ordinals. And so this ordinal, omega, we call it a limit ordinal. Think of it as like a hyperjump. That's what Noah Singh was talking about. It's like after all the naturals, then you go, woo, and you hyperjump to omega. Okay. You can in fact define omega as the set of all ordinals less than omega. Which is a crazy thing to do, but that's what people do. What comes after omega? Omega plus 1, omega plus 2, omega plus 3, omega plus 4. All of those are successor ordinals because they come immediately after another order. Can I get a head nod? What happens after all the ordinals of type? What happens after all of those ordinals? Then we get omega times 2, then omega times 3, then omega times 4. I'm skipping ahead like all of those are limit ordinals. How about after all the ordinals of the form omega times n, then we get omega squared. Then omega squared plus omega squared plus omega times 2, omega cubed, omega, and you get all the way up to freaking omega to the omega, which if you want to understand, you can somehow, but I forget. But I used to know this. Omega times omega is kind of like
prime factorization? Doesn't it work?
what is it?
If you like Dude's prime factorization.
Yeah, it's like this one on the bottom of the paper, I think. But no, actually, no, I don't think so. But you're right. Let's not talk about this right now. What do we have left? 10 minutes? Oh boy, no, 15. I think that a really good way to understand ordinals is with chess. Okay, yeah.
So are all ordinals countably infinite?
No. Every ordinal we have discussed so far is countable, and by that we mean its cardinality is it's aleph not. In fact, there are an uncountable number of countable ordinals, and the countable ordinals alone are just really big. If you go home today, don't do it. Don't do drugs, but also don't go to the Wikipedia page for countable ordinals. I think I'm getting mixed messages here. Actually don't do drugs, but you should go to the Wikipedia page on countable ordinals, which will be just crazy. You're going to have nightmares about ordinals if you read that whole thing. Yes?
First, I can confirm, if you look at the Wikipedia page, you will have nightmares. But also, are there the same number of ordinals as cardinals?
No, there are more. I believe that is true.
Wait,
Wait, hold on, wait. We only have 10 minutes left, so let's keep it light today, because we're not going to understand this fully. I do want to get back to that also with like 5 minutes left, but probably that's not going to happen. Let's talk about chess. Not regular chess, mind you, but infinite chess. Infinite chess, Mr. Rose, what are you talking about?
Oh, is that poster?
That is that poster. Yeah, so here we go. You, yeah, good. All right, so my best friend, Joel David Hampkins, world's leading expert on set theory, spent like many years investigating infinite chess and the relationship to ordinals. Okay, here we have an example of infinite chess. What's going on? Well, what's up with infinite chess? You have the board's infinite, and you maybe also have an infinite number of pieces. Okay, I claim that there is a mate in 12 here. Do you see it? Who, by the way, raise your hand if you just like don't know any chess. I'm sorry, you're gonna have a bad 10 minutes. Okay, Jeff, please explain in 20 seconds or less that mate in 12.
Move the queen up and to the right.
So like there, right?
Yeah.
And then the king can like only go there, right?
To the right.
No, sorry. Where the hell is that freaking king gonna go? Just forward, actually, right? Just forward one. Yeah, and then you just check with then you move the knight here, the rook here, something like that, and then boom, 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 boom. Yeah, okay, good. That was the worst explanation I've ever given. I think it's coming back. So anyway, you just kind of keep like, if you know chess, right, you just got to drive. Okay, obviously on a board with an edge, you can easily checkmate a king with a queen and a rook. But here it's like harder, right, because there's no edge to drive the black king towards. So what are we going to do is we're going to drive the black king towards the white king. That's the kind of high-level explanation. So repeated checks. And so since the black and the white king are 12-ish squares apart, eventually there's like a main 12 here. Okay, so you can checkmate even though it's infinite chess. Do you agree? Okay, good. Otherwise the rules are kind of the same. All right. So blah, blah, blah. What's an infinite game? 2 players. They play forever. You should think of a particular play as like an infinite, an omega tuple of moves. And there are strategies. Okay, he's like doing like real theory and stuff like that. But I just want to, he's invested in an entire theory of like infinite games and open games. Okay, so we got these ordinals. And don't even get me started with these ones on the bottom. You don't want those in your life. Okay, but we're gonna define the game. We're gonna define the value of a game as if there's a mate in 1. The value of that game is 1. And we define by transfinite recursion what it means for a infinite game to have game value, which is some transfinite ordinal. And basically, you have a value alpha plus 1 if after one move the value is alpha, something like that. Okay, so let's go. So here's kind of the idea. What does it mean? And we're gonna always have white doing the checkmating. What does it mean to say that it's white to move and the value of the game is omega squared? What that means is that no matter what move black makes, the value of that game will now be some ordinal less than omega squared. And omega squared is a limit ordinal. So it does not have an immediate ordinal predecessor. What do ordinals that are less than omega squared look like? They have the form like omega times a plus b. So just for example, maybe black plays, and now the value of this game is omega times 3 plus 17. What does it mean for the value of the game to be omega times 3 plus 17? Well, it means that white can force the value to be omega times 3 plus 16. And every time white plays, now, in other words, white has a strategy to force it to keep going down by 1. And now suddenly, it's omega times 3 is the value of the game. Now it's black to play. What that means is no matter what black does, we will now drop down like 1 level. And now we'll be like omega times 2 plus maybe some big number. And after another 2,000 moves, now it will be, we force black to play a move which will then drop the value of the game below that ordinal to like a previous ordinal. And once you drop below a limit ordinal, and if black chooses wisely, black can, make white sweat it out for like a really long time, like 10 to the 100. But eventually it'll be black to play in omega moves. And black can now do something and, you know, take the biggest number you've ever heard of, but still after that many finite moves, then white will just like whip. Okay, let's look at some examples, shall we? Blah, blah, blah. Okay, so infinite chess, infinite edgeless chessboard. All the pieces do the same thing. There's no starting configuration. There we go. Okay. You can only have one king. There's no boundaries, no ampersand, no castling, there's no blah, blah, blah. Don't do the 50 move rule, because in fact we're going to have like, you know, billions of moves. If black can, okay, let's keep going. All right. Checkmate occurs. Okay. All right, let's go. This, I claim, is actually one of the harder ones to see. This, and if you want to study this more carefully, you could, there's a poster that's been up there for years. This game, I claim, has value omega. Okay, what does that mean? This gives some kind of concrete meaning to the ordinals, I guess. It means that it's black's move, and at best, black can keep this game going for a very large natural number of moves. Okay, what if black does something like really dumb? What can white do? I think there's like a checkmate, right? Like happening right here. If white moves the queen right there, there's going to be a checkmate. So black better do something. Black better create an escape square. And the only way to create an escape square is, Ryan?
Yeah, so moving the rook.
But the middle rook up, right? Yup.
And everything
So
else just loses one move.
if he moves it up just one, right?
Yeah, or like, and anything else he does with losing one move.
You know what? Yes, right. Anything other than moving this middle rook up the board, it will be mate in one. But if black moves this middle rook up the board, say 1,000 spots, well now white can check, and then the king has only one escape square, which is to go to the spot that the rook vacated. And now, I guess, more things happen, etc.,
Just
etc.
follow along with the rook and the queen.
And you just kind of like, now you just basically like chase performing checks with the rook and queen, the black king up the board, until eventually the black king will run into the rook, his own rook. And that will form a kind of a barrier. Are you guys following this? Okay, so he can put this off very far. If he moves the black king up like 20 spaces, then it'll be mate in 20. If he moves it up 1,000,000 spaces, it'll be mate in 1,000,000. But no matter what black does, it's going to be mate, and he gets to decide by sort of dropping down from this limit ordinal. Yes.
So what happens if you move the middle rook to the right one square? I don't see a mate.
If you move the middle rook to the right by one, I don't know. Right. Chess question. What if you move the middle rook to the right one? Isn't it then it's also like, it's like an even easier mate maybe? Because then I think it's just like check with the queen and with the rook, something like that?
Then move the king to the right.
Move the rook to where?
Move the middle rook to the right one square.
Okay, we can play with this later. Do you get the gist? Good, more. Oh yeah, and he does this little these are all individual slides. He's a crazy guy. Ta-da! Okay, good. Get it? Say get it. Okay, good. Let's do some more exciting ones. All of these, he claims, have value omega. What is happening here? Oh my gosh. Here, there is like a kind of like a sea of pawns and bishops and rooks, but the rooks are all trapped inside of their own pawns. And so, white doesn't have enough material to checkmate the king. White needs those rooks, right? How are we going to get these rooks out? The only way to get these rooks out is to attack this pawn, this black pawn. But the only way to attack this black pawn is to first get that white pawn out of the way. How are we going to get that white pawn out of the way? Well, it's black's turn, so black has to do something. We're threatening to capture that rook. So does everyone see what's going on? Black's only move is to move his rook up, so like to like 1 billion spots. Then the associated pawn will capture, and then it will take white 1 billion moves to slowly move all the other pawns up, finally creating space so that he can move this pawn out of the way so he can release the rooks. Get it? And like more things like that are happening over here. Okay, good. Positions with value omega squared. What does that mean? It's pretty exciting. Let's see. Let's do this one. He's going to act it out. Okay, it's like bigger and stuff. Okay, this is called, he made hilarious little names for them all too, like releasing the hordes. Okay, what's going on? Black is screwed. Black's over here. There was a lot of queens over here. And they're back. Okay, but fortunately the queens can't get to the black king because they're on the other side of this like wall or whatever. So white needs to break through this wall. How? Well, we're going to capture this rook. If we can capture this rook, that will create like a hole in the right wall, and then we can move some of those pawns like up, and then we can like shimmy out or whatever. And then I guess something like that happens. Oh, and then we can make a space to get the bishop out. Then we can move that pawn that's below the bishop up, and then we can move the red pawn, and then we'll have space for the queens to come through, and then it's like over. Okay, so it's black's move. What can black do? Well, if black moves his rook, this middle rook, up, then this kind of starts. This gets initiated, right? But then look, white is also in some trouble because white there's this like black rook here attacking the white king. So what can happen is that black can basically harass the white king for like an infinite amount of time in between every one of white's tiny little pawn advances. Okay, and so the idea is black plays his rook to, in reality, like 1 billion, but here it's like 5. Okay, and now what does white do? White captures. I guess it doesn't matter whether you capture from the left or the right. Anyway, we've captured. Okay, now what? Now it's only a matter of time until white advances all these pawns and then get the bishop out and then move the pawns up and then the queens are out. Okay, but now what's black going to do? Black is going to check. What can white do? Well, white is now the only thing that if white just moves like here, then black can just keep checking forever and then it's like a draw, right? So the only thing white can do is just charge the rook. So white charges the rook. And black keeps checking. When white eventually threatens to capture the rook, now the rook can't check anymore. The rook must escape. And so the rook escapes to like 1 million squares away. And now that the rook escapes to 1 million squares away, now white can finally advance 1 freaking pawn. But then black initiates another round of 1 billion annoying checks. But eventually, do you kind of see what's happening? Whatever black plays, he must play down from ordinal omega to a finite ordinal. And then it takes white that many times before he's caught up to the black king. Black can't do any more checks. And so we just do this. In other words, white is forced to play omega chase rook chase downs and has to do that omega times. But eventually, white gets to move his pawns up, and then when black runs out of checks now, white can get the queen out, and then it's all over. Okay, this is omega squared times 4, because now, yeah, white has to, like, once again, we can checkmate the black king if, I don't even know. Capture, and then after omega time, we basically have to just do that 4 times, right? It's kind of like the previous game, but now 4, it's like, it takes omega squared in order for me to get 1 pawn up, but now I just have to repeat it again with these like 4. Okay, and he's gone all the way up to omega to the 4th. And he conjectures that there is for every single ordinal a position in infinite chess associated with that ordinal, I believe. You can read this paper, I'll link to it. A lot of clicking going on. My hand kind of hurts. Alright, good.
You have another test question?
Yeah, it's just a presentation with 500 slides. Okay, 503. Not the greatest explanation of ordinals ever. You thought it was good? Good, yeah. Perfect, yeah. Thank you. Oh, there's also 3D chess, infinite 3D chess.
Are you gonna post
Oh, this is the problem from the opening slide.
Can you post this?
I will. Yep, I absolutely can. And I will.
Are you just gonna turn on one? What?
Yeah, infinite number of knights are not enough to checkmate in infinite chess. Okay, good. That's over. Goodbye, period 3.